Hello everybody. In this video we're going to continue working with Chapter 2 functions, specifically 2.6 partial fractions. So we know that in arithmetic, when we add fractions, we find the least common denominator and multiply both the numerator and denominator of each term by what is needed to complete the common denominator. For example, let's say we are adding 2/3 plus 5/7. Well, we know that the common denominator is 21. Therefore, we multiply this by 7/7, and we multiply this other term by 3/3. We get 14 plus 15 over 21, and that finally gives us 29 over 21. Another example where we add three terms. In this case, the least common denominator would be 27. Therefore, we multiply 2/3 by 9/9, 5/9 by 3/3, and we add 1/27 to that. So we get 18 plus 15 plus 1 equaling 34 over 27. So what we're going to study in this section is reversing this process, which is actually expressing each compound fraction as partial fractions. This is what is called partial fraction decomposition. And the method of partial fractions decomposition is extremely helpful in evaluating certain integrals, which is something we're going to study in integral calculus. With partial fraction decomposition, we're going to reverse the process and decompose a rational expression into two or more simpler, proper rational expressions. This is a very useful skill in which a single fraction with a factorizable denominator is split into the sum of two or more fractions. Those are the partial fractions, whose denominators are the factors of the original denominator. So here we have an example where 12x minus 1 over 2x squared minus 5x minus 3 can be decomposed into 2 over 2x plus 1 plus 5 over x minus 3. Now notice that 2x plus 1 and x minus 3 are the factors of the denominator. So we're going to learn how to do this. Very well, so here we are in example 2.31, and it says find the partial fraction decomposition of x plus 1 over x squared plus 5x plus 6. So the first thing we have to do here is factor the denominator. So notice that this is the same as saying x plus 1 over x plus 2 times x plus 3. So what we do is then decompose this by saying that x plus 1 over x plus 2 times x plus 3 would be equal a over x plus 2 plus b over x plus 3. So then we would notice that this is the same as saying a times x plus 3 plus b times x plus 2 over x plus 2 times x plus 3. Therefore, we can solve the equation x plus 1 is equal to a times x plus 3 plus b times x plus 2. And then here we can plug in values to our convenience because since this is an identity, the two sides must be the same for any choice of x. So for instance, if I want to solve for a, I can say, well, let's make x equal to -2. And then I substitute x with -2, and I'm going to get -1 is equal to a plus b times 0. Therefore, a is equal to -1. Now notice that we can just rewrite this again. So x plus 1 is equal to a, which we know is -1. So we can just substitute that for -1. -1 times x plus 3 plus b times x plus 2. So in fact, we can just plug anything at our convenience here. For example, we can plug in -1. So let's say x equals -1. We're going to get 0 is equal to -1 times 2 plus b. So that means that b is equal to 2. Therefore, we can say then that x plus 1 over x squared plus 5x plus 6 can be decomposed into negative 1 over x plus 2 plus 2 over x plus 3. In the following slide, you're going to see a few cases of partial fractions. First, when the denominator is quadratic, this is the case we saw first, and it's when you have a quadratic denominator that factorizes into two distinct linear factors. So you can see this, they're distinct. So this is the case where you get a over the first linear factor plus b over the second linear factor. Then we also saw the case where the denominator is quadratic, but it factorizes into repeated linear factors. And then you can see that that can be split into this here. You have this expression where you repeat the squared factor that you had in the denominator, but you also have to take into consideration the other case where it might just be linear. And then we solve for a and b. And finally, we have another case where the denominator is cubic and it factorizes into three distinct linear factors. Also, in every case, the numerator is either constant, linear, or quadratic. So notice that this one we would split into three fractions, and we would have to solve for a, b, and c. So next we have example 2.32, and it says decompose the rational expression 5x squared plus 16x plus 17 over 2x cubed plus 9x squared plus 7x minus 6 into partial fractions. So again, the first thing we have to do is factor the denominator. Now, this is cubic, so we know it has three roots. So the possible roots of this polynomial are going to be the factors of 6 divided by the factors of 2. So notice that 6 can be divided by plus minus 1, plus minus 2, plus minus 3, and plus minus 6. And then 2, plus minus 1, and plus minus 2. So then dividing these and getting all the combinations, we would get plus minus 1, plus minus 1/2, plus minus 2, plus minus 3/2, plus minus 3, and plus minus 6. So these are all the possible real factors of this polynomial. So what we're going to do is make use of the remainder theorem and see which one gives us a remainder of 0, or which one of these is a root just by plugging it in, right? So notice that if we plug in negative 1, if we do the mental math, it's not going to work. 1 is not going to work. Let's test with negative 2. So let's say 2 times negative 2 cubed plus 9 times negative 2 squared plus 7 times negative 2 minus 6. So this is going to give us negative 16 plus 36 minus 14 minus 6. And notice that this will give us 0. So that means that x plus 2 is a factor. So I'm going to use long division to find the other polynomial, right? X plus 2 dividing 2x cubed plus 9x squared plus 7x minus 6. So here we multiply by 2x squared, right? So we're going to get 2x cubed plus 4x squared. Subtract. I'm going to get 5x squared plus 7x. So that means that we have to multiply by 5x. And from here, we're going to get 5x squared plus 10x. Subtract minus 3x. Bring down the minus 6. And then here we multiply by minus 3. and we get minus 3x minus 6, subtract, remainder is 0. The important thing here is that we get this here. So that means that the original denominator expression is going to be x plus 2 times 2x squared plus 5x minus 3. And this is easy to factor. Notice that this is simply going to be 2x minus 1, 2x minus 1 times x plus 3. So we have factored the denominator. So next, what we're going to do is decompose it into partial fractions. So we have then that this is equal to 5x squared plus 16x plus 17 over 2x minus 1 times x plus 2 times x plus 3. And then we can decompose this into a over 2x minus 1 plus b over x plus 2 plus c over x plus 3. So from here, we can get that 5x squared plus 16x plus 17 is equal to a times x plus 2 times x plus 3 plus b times 2x minus 1 times x plus 3, and then plus c times 2x minus 1 times x plus 2. So I'm going to do what we did before, which was just plug in a convenient value on both sides of the equality. So notice that here we have x plus 2 and x plus 2. So if I say x equals negative 2, and I plug that in here, what I'm going to get is 5. So 5 is going to equal, this will be 0, and this will be 0. So I'm just going to be left with b. So it's going to be, notice that I'm going to get negative 5 from here, right? Because this is 1, this is a 3, so it'll be 1, negative 5b, so negative 5b. So we have a solution for b. That means that b is equal to negative 1. Notice that if we plug in negative 3, we can get rid of this and rid of this and solve for c. So let's say x equals negative 3. Plug in negative 3 there, and we're going to get 14. So 14 is going to equal 7c. Therefore, c is equal to 2. Let's notice how we get 7 from this here, right? Because if we plug in negative 3, we would get negative 1 times negative 7, which is 7. Okay. And then the other one we can use is 1/2, right? If we say x equals 1/2, plug it in there, and we're going to get 105 over 4. So this is going to equal now. Notice that this will be 0, and this will be 0 here as well. So we're only going to be left with a times x plus 2 times x plus 3, which is 1/2 plus 2 times 1/2 plus 3, and that's going to give us 35 fourths a. And then here, solving for a, we're going to get that a is equal to 3. So that means that we can now substitute here for a, b, and c. And we said that a is 3, so 3. B is negative 1, so we should probably change the sign here. B is negative 1, so negative 1. And for C, we got 2. So this would be the decomposition into partial fractions. So in the next slide, we're going to take a look at a couple of examples of other situations. So first we have the case of repeated linear factors. If the denominator of the rational expression contains repeated linear factors, then following our discussion in the introduction, the process is as follows. So here we have this example where there's a polynomial that is being divided by x minus 1 cubed. So this is the repeated linear factor. This times 2x minus 5. So in these cases, we have to consider all the possibilities with the linear factors. We would have to consider x minus 1 cubed, x minus 1 squared, and x minus 1. And then finally, 2x minus 5, which comes from here. So this is what we would have to solve in this case, right? We'd have to find A, B, C, and D. Now notice that it may turn out that any of these numbers could be 0, especially B and C. Okay, so the next case is when we have irreducible quadratic factors. If the rational expression we are decomposing contains irreducible quadratic factors in the denominator, then the numerator could have a linear and or a constant term. So for every irreducible quadratic factor in the denominator, we will need a linear term and a constant term in the numerator. So what does that mean? Well, for example, if we get this case here where we have x minus 1 squared, we know that this is a repeated linear factor, so we know what to do. We see it here. But in this case, this is irreducible. We cannot reduce this by factoring. So then that would require an expression in the numerator, like this one, that would have a linear factor and a constant term. So this is the linear factor and this is the constant term. So then we would have to solve for A, B, C, and D. So next we're going to do example 2.33, which will be the last one on this video. So it says write 3x minus 1 over x squared plus 4x plus 4 as the sum of partial fractions. So notice that this is just a perfect square, so we can rewrite this as 3x minus 1 over x plus 2 squared. So this is a case where we have a squared denominator. So notice that this is the same as saying a over x plus 2 plus b over x plus 2 squared. And then if we multiply both sides of this by x plus 2 squared, we're going to get that 3x minus 1 is equal to a times x plus 2 plus b. So this one's easy to solve because we can just say let x equal negative 2. And then from there we're going to get negative 7 is equal to b. We can rewrite this then as 3x minus 1 is equal to a times x plus 2 minus 7. And we can solve for a just saying let x equals 0. So minus 1 is equal to 2a minus 7. So 6 is equal to 2a. Therefore, a is equal to 3. So that means that we have the solution because b is negative 7 and a is 3. So all we have to do is just substitute a and b here. And notice that we get 3 here and minus 7.